Welcome to the lesson on the product rule. So recall from previous lessons that we had the rule the derivative of f at x plus g at x was the derivative of f plus the derivative of g, and we called that the sum rule. Then we had the difference rule, which was the derivative of f minus g, which was just the derivative of f minus the derivative of g. So now we want to get a product rule. So essentially, what is d by dx of f at x times g at x? So what is this? Now, question mark, what does this equal? Probably, look at these two rules, a good guess would be, well, can I just do the derivative of x times f at x and then just multiply that by the derivative of g at x? So there's a question, right? Is it this? Are these two things equal? And the simple answer is no. That rule doesn't quite work for products. The rule is not quite so easy. And usually we'll just kind of illustrate it with a very simple example. So consider this. Let's say f at x is x and g at x is x squared. So what is f at x times g at x? The product of these two functions would be x times x squared, which would be x cubed. Okay, so the product's over here. So now if we wanted to do the derivative, f at x, g at x, the derivative of this product, well, that's clearly just the derivative of this, which we know is 3x squared. So the derivative of the product of f and g is 3x squared. So now let's check. Is that equal to the derivative of f times the derivative of g? Well, what's the derivative of f? Well, the derivative of f is 1, and what's the derivative of g? The derivative of g is just 2x. So therefore, the derivative of the products is just equal to 1 times 2 at x, which is 2 at x. Now clearly these two things are not equal. So that should tell us that this guess we had up here is not the case. This rule does not hold. So the rule must be something different. Now, just to try to ease your worries, if you guess that and you feel bad now about guessing the wrong thing, don't feel too bad. I think the story is that Newton or Leibniz, they guessed the same thing. So they thought that would be the rule too. And then they obviously tried a couple and didn't quite work out. So they figured out it must be something different. So what is the rule? That's the question, right? The product rule. I think for this video I'm just going to give you the rule first, and then I'll just do a very sort of brief sort of proof, which isn't quite rigorous. So if f and g are functions, then technically I should say are differentiable functions. Then how do we write this? F at x, g at x, I'll use Leibniz notation. Then the derivative of f at x, g at x is equal to, so it's not just the derivative of f times g, it's equal to do the derivative of the first one of f at x, but then you multiply that by the second one without differentiating, and then you add that to, you leave the first function and then multiply that by the derivative of the second function. Okay, so as a way to remember it, it's the derivative of the first times the second plus leave the first times the derivative of the second. So it's not an example. Let's do a little very quick proof, just sort of an outline of the proof. So if f, if we have the function so our function is f at x, f times g of x. So we want to get the derivative of this. So if we don't have a rule, the only way to really do it is to use first principles. So by first principles, that'd be the limit as h goes to 0 of the function. So that'd be f times g at x plus h minus f times g at just x all over h. So what is f times g? Well, that's the way we write that is just f at x plus h times g at x plus h minus f at x g at x all over h equals, okay, so now the question is, what do we do from here, right? How do I simplify this? And it's not obvious at all what you would do, but there's a little trick, and that's to sort of just make this function look a little different. And the trick, when you see the trick, you're going to say, well, how would I know to do that? And the answer is, you probably wouldn't have. But what we're going to do is we're going to subtract, we're going to sort of insert two terms, but the two terms will cancel out. So we're going to insert minus f at x, g at x plus h, and then we're plus f at x, g at x plus h. Okay, so notice that this right here, with the negative, is really equal to 0. So it's okay for me to just kind of put that in the middle because it's equal to 0. Right? So all I did was I took this original thing and I stuck these two terms right in the middle, but these two terms are equal to 0, so that's why I can do that. And like I said, you're probably saying, how did you get those two terms? It's not obvious, but it works, so that's what we do. So now what we're going to do is group some terms. I'm going to take this term here, and I'm going to group it with, well, no, sorry, actually the way they're grouped's good. What I'm going to do is I'm going to factor. So notice that what do we have common to these first two terms? So just look at the first two terms as a group and the second two terms as a group. So I have a g at x plus h common, so I'm going to factor out a g at x plus h, and just because I know where I'm going, I'm going to write that at the back instead of at the front like we normally do. Be f at x plus h minus f at x. And then what do I have common to these two? I have an f at x common, so I'll do this one at the front, because again I know where I'm going. This g at x, so I just common factored, all divided by h. Now what I'm going to do is I'm going to apply one of my limit laws. So this is the limit of this plus this. So I'm going to break it up and write it as two separate limits, which if you remember from limit laws is okay, provided those limits actually exist, which technically would require a little bit of justification, which is one of the reasons this proof is not quite as rigorous as it could be. I'm just saying that you can do it. I'm saying these two limits are going to exist, which technically you should actually show that they have to exist. Okay, so now what I'm going to do is, well, again, I'm going to break things up a little further. I'm going to take this part and this part, and I'm going to separate them into the product of the limits. So that's again a limit law. So I can take the limit of this and multiply by the limit of this, provided those limits exist, but again, same reason as before, we're going to kind of assume they do. Plus, and then I'm going to do the same thing here. Uh-oh, battery's dying. Almost done, almost done. Okay, now look at this. What is this? That's our definition of f prime. Right? This is by definition the derivative of f. In this one, if I let h go to 0, what would I get? I get g at x plus 0. That's just g at x plus limit as h goes to 0 of f at x. There's no h there. That's just f at x. Then I'm going to let and then I'm going to look at this. What is this? That's the definition of g prime. So there is our product rule. So we proved it. Sort of.